going to see the magnitude and phase response of a piezoelectric sensor. So this is the input oscilloscope and this is the output oscilloscope. First, we are to the input oscilloscope. We are going to send an input signal to the piezoelectric sensor. This is the connection, and then to an output source, output signals. We are going to send it to the another oscilloscope. Here we can see two sinusoidal waves. One is the input signal sinusoidal wave, and another the blue yellow one is the input sinusoidal wave, the one which is sending to the piezoelectric sensor, and the blue represents the output of the piezoelectric sensor. This purple graph shows the FFT, that is in the frequency domain, the output of the sent by the piezoelectric sensor, and this shows the magnitude and phase response of the piezoelectric sensor.
Here we can see the two sine waves. The one is yellow sine wave which represents the input, and the one is blue sine wave which represents the output. And also here we have the FFT graph, and the FFT graph, there is a one dominant peak which represents the resonant frequency, which means the amplitude is maximum here. And also we can see in the magnitude response graph, here we also here there is a frequency, and in x-axis and in y-axis, and in y-axis it's the gain which is in dB. And here we can also see one peak which represents the same as we saw in the FFT graph here. After that we have the phase response graph, in which the x-axis is the frequency and y-axis is phase difference. Here where we can see the sharp turns, it represents the resonant frequency. Here we can say it here it's on 6000, 8000, 12,000 and something else.
So first we will see where the gain is occurring in the graph. So as you can see, there are three significant gains in the graph. One of is 200 hertz, and second is around 1000 hertz, and the third one is around 13,000 hertz. And you can see the values of log gain of 200 and 1000 and 13,000 respectively. So we will calculate the Q factor for three of these, and let's see what's next. So what the Q factor is, it is the ratio of resonant frequency with bandwidth. High Q refers to narrow bandwidth, and low Q refers to broad bandwidth. Okay, so our step one is to identify the resonant frequency, as we have already identified our resonant frequency, which is 200, 1000, and 13,000 hertz. So the peak gain occurs at 200 hertz. So first, then we will find where the minus 3 dB point uh, minus 3 dB point below and above the peak gain. So for 200 hertz, the below close to 200 dB drop is at 150 hertz, and the above crosses where the peak crosses minus 3 dB is at 250 hertz. Same as that for 1000 hertz, which is 850 hertz for drop, and 1500 hertz where it crosses minus 3 dB. Same as that for 30. So now we'll do the bandwidth calculation. So for F1, which is equal to 220 minus 150, which is equal to 70 hertz, and F2, which is equal to 650, and F3, which is equal to 5500. F1, F2, F3 are the respective bandwidth of 200 hertz, 1000 hertz, and 30,000 hertz. So now we'll calculate the Q factor. So the Q factor for 200 hertz, which is equal to 200 divided by 70, which is equal to 2.85. Same for 1000 hertz, which is equal to 1.53. And for 13,000 hertz, which is equal to 2.63. So as we can see from the Q values of all the three peaks, the 200 hertz is the maximum Q value, and the 1000 hertz has the minimum Q value. So from the definition of Q factor, we can derive those two things, that the 1000 hertz has broad bandwidth and the 2200 hertz has narrow bandwidth.
we are going to see the magnitude and phase response of a photodiode. So this is the input oscilloscope and this is the output oscilloscope. Here first we are supplying 100 kilohertz of input with an DC offset of 5 volt. This is to keep the LED light switched on at all times. And so through this input signal we are sending 5 VPP. Sorry, we are sending 5 VPP. And on the other side, here we have a photodiode, and photodiode generates a current due to the light falling on it. And this is connected, the output current which is generated is connected to another oscilloscope. Here we can see in the display of the output oscilloscope, the yellow signal shows the input signal that we are supplying, and the blue color shows the output of the photodiode. And here we can see the FFT, fast feedback. This is the output signal in the frequency domain. And here we can see the magnitude response, which corresponds to the FFT which is shown here. And here we can see the phase response, and we can see there are multiple peaks and troughs.
So here we can see the two sine waves. The one is the input sine wave which is yellow in color, and the blue color is the output sine wave. And also we see here the FFT graph of the output signal. Here it represents the gain in dB, and here it represents the frequency in kilohertz. So the 3 dB cutoff frequency is approximately around the 140 kilohertz because the graph decreases here. Also we can see in the magnitude response graph, here also the 3 dB cutoff frequency is here because the graph decreases here. And in the phase response graph, here the phase response graph expresses the delays at different frequencies. So the less delay means the at lower frequency there is the less delay, and at higher frequency there is the more delay represents.